Okay, we're going to take a look at factoring methods, specifically greatest common factor, extraction, difference of squares, and trinomial factoring. So let's go ahead and take a look at our first example. K squared minus 2k. Do we have a greatest common factor, a GCF? Yes, we do. We can extract a k from each term. This is also known as undistributing, and our check step shows that if we distribute k times k minus 2, we end up with our original expression. Number 2, x squared plus 9x plus 18. You should recognize that this is a quadratic form, meaning that we have our variable squared as our first term, a regular variable to the first power, and our third term is a constant. So what we're going to do is we're going to ask ourselves, what two numbers multiply that give us 18 that add to give us 9? Well, the answer is 6 and 3, because 3 times 6 is 18, and 6 plus 3 is 9. Therefore, our factored form is two binomials, x plus 6 times x plus 3. If we were to FOIL, multiply these back together, we end up with our original expression, x squared plus 9x plus 18. Let's take a look at number 3. Remember, always factor the GCF first. The GCF is 6x. Therefore, we divide each term by the GCF in order to find out what is left over. 6x cubed divided by 6x is x squared. 16x squared divided by 6x is 3x. And negative 60x divided by 6x is negative 10. So we're looking at 6x times the trinomial x squared plus 3x minus 10. Now we're not done yet, because this trinomial is factorable. Well, it should be factorable. Let's take a look. We're looking for two numbers that multiply that give us negative 10 that add to give us 3. Well, let's try 5 times negative 2. 5 times negative 2 is negative 10, and when you add 5 and negative 2, we get 3. So it's sort of like one of these x situations up here. When we FOIL it back out, we end up with x squared plus 3x minus 10, which is our original trinomial. And if we were to distribute the 6x throughout this trinomial, we would end up with our original expression, proving that we have factored correctly. Okay, our fourth example. This follows the format of a difference of perfect squares. Difference means minus, and perfect squares means x squared is a perfect square, and 81 is a perfect square. The answer is always a binomial with each leading term as the square root of the first term, so square root of x squared is x. And the second terms is the square root of 81 of the second term in the original expression, which is 9 and 9, and the signage is always 1 plus and 1 is minus. If we were to FOIL this out, you would see that the O and the I terms cancel. We're left with x squared minus 81, which is our original expression. Let's look at a few more examples. Here's Sage and Scribe number 1. So we have x to the 4th power minus 81. Can we factor a greatest common factor? No, we cannot. There is none. I'm going to recognize that this is a difference of squares. So first term is x squared. Last term is 9. And the signs are 1 plus 1 minus. Okay, you may think you're done, but you have to examine each binomial to see if we can factor any further. So here we see we have x squared minus 9, which again is a difference of squares. So our first factor of x squared plus 9, we can't do anything with that. That's prime, so we just bring it down. X squared minus 9 can be factored out to x plus 3, x minus 3. Number 2 is slightly tricky because it's out of order. First thing I'm going to suggest is reorder it so that we have our highest exponent, the highest power leading, and we descend down to the lowest power. So negative x cubed minus x squared plus 6x. Is there a GCF that we can extract? Yes. So let's go ahead and factor out negative x. When we factor out negative x, we need to divide each term by negative x to find out what's left over. Positive x squared plus x minus 6. Can we factor any more? Well, this looks like a trinomial. Let's see if we can find two numbers that multiply to give us negative 6 that add to give us 1. And yes, we do. We have 3 times negative 2. So our final answer is negative x times x plus 3 times x minus 2. All right, we skip to number 4. Here we're looking for a GCF. There is none. X squared plus x plus 1/4. This does follow the trinomial pattern. Our first term is x, because x times x is x squared. The second term of each binomial is 1/2, because 1/2 times 1/2 is 1/4. And since both terms are positive, this one's an easy one, they're both positive. Now it's best to write your final answer in simplest form, which is x plus 1/2 quantity squared. Number 5, so we have a trinomial. There's multiple variables here. There's a and b. Is there a GCF we can factor out? Yes, it's in the coefficient. It's 3. So we divide each term by 3. We end up with 3 times the trinomial 4a squared plus 4ab plus b squared. The GCF just comes down to the final expression down here. And let's multiply, or let's find what two numbers multiply to give us 4a squared. That's 2a. What two numbers multiply to give us b? That's, or b squared, that's b. And everything's positive, so we have plus signs. So in our check step, we want to FOIL back out. 2a times 2a is 4a squared. 2a times b times 2a is 2ab. And 2ab, when you add those together, we get 4ab. Finally, b times b is b squared, so we have confirmed that this is the correct factorization. Last one. Let's factor this one completely. Let's look for a greatest common factor. 12 and 75. Well, 2 doesn't work because 75 is odd. 3 works because 3 times 4 is 12 and 3 times 25 is 75. So let's go ahead and start with 3. The variable part, t to the 8th and t to the 4th, yes, we can factor out t to the 4th because we're looking for the greatest common factor. So we're going to factor 3t to the 4th power. Dividing both terms by 3t to the 4th, we end up with 4t to the 4th power minus 25. Are we done? Not quite, because this binomial here follows the format of the difference of squares. So we're going to take the square root of the first term, which is 2t squared, and put them in the beginning of each binomial. And the square root of 25 is 5. We're going to put those as the second term of each binomial. And as you can see, we have 1 plus, 1 minus, because that follows the format of difference of squares. And here's our final factored form. Good luck to you.